Okay, if you're looking at this video, it is probably because you have jumped online to take the quiz. That's an important deal. And you've watched the lesson on the net change theorem. You've figured out that an integral is an area accumulator. You've talked about how to use velocity to find displacement and distance. You've talked about how to turn rates into amounts. You've taken a look at this crazy question maybe, and you've tried these questions, and that's what this screencast will focus on. This screencast will focus on the questions that were in that worksheet, um, which are interesting questions because they aren't obviously calculus questions, and yet here we are. So you're given a question about a rate. This is a rate. It's in gallons per minute. And then here we explicitly ask you to find the integral from 0 to 4. So how do you find that integral from 0 to 4? I don't know a way to do it except to use your calculator. This would be a case where you would want to find an antiderivative. I don't know how to find an antiderivative for that function. Nobody I know does. So this is a scenario where you have to ask your machine. And your machine is going to give you approximately 37.291. But it's in context. So 37.291 what? Well, this rate is in gallons per minute, and time is in minutes. So when we add up the areas of a bunch of rectangles, and these are the heights of these are the units for the heights of the rectangles, and these are the units for the bases of the rectangles, well then this is a number of gallons. What does this mean? In context, it means that in the first 4 minutes, 37 gallons of water were sprayed on the field of vegetables. And that's how we would write it. I don't have space to write it here. You have space to write it on your sheet. Uh, in context, so we talk about what this means in the first 4 minutes of spraying. We talk about what this number means with a unit. There were 37.291 gallons of water sprayed on the field of vegetables. So we talk about what this means in context. We talk about what this means in context. We use units. Then we did this question. This is another question about a rate. This is measured in people per hour. So this is people per hour, and this sort of makes sense if you think about how an amusement park looks in a particular day. Not a lot of people coming in initially, and then as the day goes by, lots and lots of people come into the park. And then toward the end of the day, there aren't a lot of people showing up at the park looking for entrance. So this makes sense in the context of the problem. So P is measured in people per hour. We're going to use a definite integral over a 12-hour period. So we're going to use a definite integral over a 12-hour period. We have our people rate function. This is something you could work out by hand, but we won't. The calculator is going to give us about this number. Now, what does that number mean? This is measured in people per hour. Time is measured in hours. So when we add up a bunch of areas of rectangles, and this is the unit of the height of the rectangles, and this is the unit of the base of the rectangles, then we get an answer, and that answer is a number of people. This is the total number of people that enter the park during that 12-hour period. This question assumes that nobody leaves the park. Maybe it's one of those parks you're not allowed to leave. Well, and why would you? You're having fun. So here's the temperature changing. No, this is not a temperature changing. This is a function that describes the temperature and how it fluctuates in the course of a particular day. You're supposed to find the average temperature. So this is temperature. We're looking for the average temperature. Well, what does that mean? It means that if we plot this function and take all those y values at every moment of every day, every moment along that particular day, what's the average of them? So how do we add up infinitely many things and take an average? Well, we take an integral from 0 to 24. That allows us to add infinitely many things. Sort of, kind of, not really, but that's the rough idea. What are we adding? We're adding all of these. And once we add those, to find the average temperature, we divide by how long the interval is. If you have a function that measures temperature and you are looking for the average temperature, we integrate and divide by the length of the interval. So what is that? Well, your calculator is going to tell you that that's about 40.033 degrees. And that makes sense. So hopefully you looked at this question. This was question 10 on a final exam in years past. You won't find it anywhere else because I wrote it just for this. It doesn't exist on the internet anywhere. So the depth of water in the Springfield Ocean rises and falls over the course of a day. This is the rate of change in the depth of water, and this is measured in centimeters per hour. Time is measured in hours. Time equals 0 represents 6 a.m. So there are some parts of this question that are about net change, and there are some parts of this question that ask us to interpret what rate of change means. Is the depth of the water increasing or decreasing at noon? Noon is time equals 6. So is the depth of the water increasing or decreasing? Well, if we had some function that described the depth of the water, we would want to know if its derivative was positive or negative at time equals 6. Well, this is the derivative of the depth of the water function. So we want to know if r of 6 is positive or negative. And because we have a machine, we know that r of 6 is about 0.550, and that is positive. So the depth of the water is increasing. So there was a part of the question where I asked my students to interpret this as a derivative. Then I asked my students to do the net change thing. According to the model, how much higher will the depth of the water be after a day has passed? So this is the rate of change of the depth of the water. We're interested in a change of depth in centimeters. So it stands to reason we take an integral over an entire day of this r function. If we do that, how do we do that? We take an antiderivative, which would be the depth of the water, sub, and subtract. Well, what does that mean? We figure out what the depth is at 24, we figure out what the depth is at 0, and subtract. That's how much higher the water will be after a day has passed. So this is the mechanism that we use. Our calculator does this for us. We can take an integral from 0 to 24 of this hard to type in function, and the calculator gives us 12 point, oh really, 1.2 point, yes, wonderful. 12.5796, and we were asked to round to the nearest centimeter. And again, this makes sense. This is measured in centimeters per hour. This is measured in hours. We multiply them together. We get an answer in centimeters. So last piece. When is the depth of the water a maximum? And we're only considering things on a closed interval. So we're trying to find a maximum on a closed interval. And that means we have to know what the depth of the water was at 0, what the depth of the water was at 24, and what the depth of the water is anywhere there's a critical point. So we're just going to pretend, for argument's sake, that we're going to let this be the initial condition, the 0 condition. So we know that the integral from 0 to 0 of r of t, that's 0, and we know what the condition is at 24 hours. We know we are 12.5796 centimeters up from where we were. The question is there a time between 0 and 24 when we are higher than that? So we take normally, if we're looking to find a maximum on a closed interval, we take a derivative, set it equal to 0, and solve. Well, what's the derivative of an integral function? It's this. So we are looking for where r of t is 0. This is the derivative of the function that measures the depth of the water. So this happens, you can figure this out on your calculator at time equals 6.65212 or 17.3479. These are critical points. These are places where r is 0, r is the derivative of the function that measures the depth of the water. So we figure out the integral from 0 to 6.652. And we figure out the integral from 0 to 17.3479. And it turns out that this one is almost 16, and this one is very not. So what's the biggest? That's the biggest. So this is the time when the depth of the water is a maximum. That's the time when the depth of the water is a maximum. Show the analysis. We have taken a derivative, found critical points, checked the endpoints, checked the critical points. That's the biggest. So this is the answer to the question. That's the time when the depth of the water is a maximum. Okay. Hopefully, I will see you in office hour if there are questions about this. Hope that all is well with you and yours. See you soon.